Okay.
All right, here we are. Our next topic is the rates of change here. And we have to begin with the average rate of change. This is defined this way. The average rate of change of F over AB can be found using this quotient. If we want to find the rate of change at a particular value, this is called the instantaneous rate of change. And we would use a derivative to get that. This comes into play when we have, for example, a position function defined by S of t. And we want to find perhaps average velocity versus instantaneous velocity. So this would give us our average velocity from time t0 to t1. And this expression would give us our instantaneous velocity at any given moment of time. So there's one's an average and the other one is actual instantaneous. So let's see how that works in our next example. Okay. To do this example, we're going to use this derived formula for the position of an object free falling under the influence of gravity only. So this is considered straight, an object moving in a straight line from someplace above the ground, heading straight to the ground. And g is the acceleration constant due to gravity, 9.8 meters per second, or 32 feet per second. V0 is initial velocity, and S0 is initial height. This would be given for a given context. Okay, now, so here is a position function. Now notice that I'm calling it f of x. It doesn't have to be in t, but in any case, the average rate of change, let's go ahead and compute that. We need to find f of 5 minus f of 2 over 5 minus 2. That will give us the average rate of change. So we're going to have to put these numbers in here. 3 times 5 squared minus 4 times 5 plus a 5 minus, we have a 3 times 2 squared minus 4 times 2 plus a 5. All of that over 3. So it looks like we have 75 minus 20 plus a 5 minus, inside here we'll have a 3 times 4 is 12 minus 8 plus a 5 over 3. And let's see if we can get this down here. We'll have, let's see, 80 minus 20 is 60 minus, looks like we have 17 minus 8 is 9 over 3, which makes, we have, let's see, 60 minus 9, that's 51 over 3. And that's actually a 17, isn't it? Okay, so the average rate of change is 17. Now let's look at the next piece here. The rate of change at a particular point, x equals 4. Rate of change is f prime of 4. That's what we need. So we're going to use that function of x. We need our derivative first. So we want f prime of x is 3 times 2 x minus 4 times 1. That is 6x minus 4. F prime of 4 is 6 times 4 minus 4, which is a 20. That is instantaneous rate of change. Okay, now here we have a position function. Stone dropped from the top, pool of water. How high is the building? The stone makes a splash 5.6 seconds after it's dropped. We may not actually need calculus on this one. I'm not sure, but let's look at the example here. Okay. Okay, so what's missing is how high. In other words, this is what's missing, the S sub 0. The initial speed of the stone is 0 because it was not thrown off the top of the building. It was simply dropped from rest. It was not moving at all initially, and then it was dropped. So that's a 0. So what we have is this function. We have S of t negative 4.9 t squared and plus S sub 0. Okay. And okay, so it's dropped, and we know 5.6 seconds later, you hear the splash. Well, you see the splash. You don't hear it, you see it. Okay, now we're going to assume that the time that it took for you to see that splash was negligible. Okay, although technically speaking, if you remember physics, it takes a little bit of time for that light to travel from the pool up to the person at the top, if he sees it, or maybe a person's watching at the bottom. Who knows? Okay, so in 5.6 seconds, we would have our height S of 5.6 equals S0. That would be the height. Okay, because it had to go that far, it traveled that far in that amount of time. Okay. Let's see, S sub 0, and that's actually, let me back up a little bit. Okay. And so S sub 0 plus, well, not plus, that had to be a minus. Minus, I'm going to write this backwards here, but okay, minus 4.9 times that 5.6 squared. So that tells us that S0 will be equal to that 4.9, 5.6 squared. On calculator, that turns out to be okay. So if we want to find the speed at the bottom, so we found the height, but this is an extended question here. What would the speed of the rock be, the stone, when it hits the water? We would have to find the derivative of this function, the rate at which this is changing, the speed, the function, the way at which the position is changing. That would be the speed. That's the derivative. So we would find S prime and then calculate here. This ends up being, let's see, 9.8. It's negative 54.9. That would be meters per second. Now it gives us our negative because it's in a downward position. So it is at that point. Let's see now. You could also calculate the acceleration at that point. If you did that, you would find another derivative. Acceleration is the rate of change of the velocity. So we would take another derivative of this one, which I'll just for now, I'll call it S double prime. We'll talk about that later a little more, but for right now, taking a derivative of this function, and it's negative 9.8. And that's the acceleration due to gravity. So it's the same acceleration at any point along the path. That's not changing. Constant acceleration. Okay, so I believe that's about it for this one.